this lesson. We have installed and downloaded the data with the Boston dataset. I've shown you how do you load it from the CSV. Part of the reason I use CSV instead of the scikit-learn toy dataset, although they're exactly the same, really, is that the CSV is probably more likely to be the more common way that you extract data from the real world. So hence the reason why I want to demonstrate that over the scikit-learn. In saying that, however, I have included some codes on how you can actually load it. It is in between. I don't have a lesson to cover that, although I provided some documentation that you can refer to in this notebook itself for you to actually explore around. Right, let's start with this, and we've already run the file, we've already run and loaded it onto the RAM. So I'm going to run the script, which basically is a Python pandas libraries, very quick descriptor statistics for each of the features that we have. So you can see here for each of them we have basically input count, or rather a count of 506 rows of data or 506 samples. We have the mean of each of the columns, the standard deviation, the minimum, the maximum, and then also each of the 25th, 50th, and 75th percentile. And that gives you a really broad overview of things. Now, what would you look for? Now, this is the part whereby you do need some statistics background, which I can't cover in this course itself. The couple of things that I do want to point you to, although we can't cover everything, is the first thing is you can look at the means. Not the most accurate way of telling where the middle part is. You can of course augment it using the median, which is also the 50th percentile. You can see the mean here is 3.61. The median, however, is 0.25. You can see they're vastly different. That tells you this data is not, or at least for this column of data, it's not very normal from the perspective of normal distribution. Again, I have to refer you to some statistics reference, and I need to trouble you to actually go and look it up yourself to understand what that actually means, because that will have a bearing in terms of how we actually create our model or machine learning model to replicate or emulate or to describe the underlying data. At the end of the day, machine learning is really about creating an algorithm that mimics the underlying data, the behavior of it. So we do need to actually have a fairly good understanding of the behavior of the underlying data or whatever that's generating the data to be able to create a reasonably useful machine learning algorithm. Okay, so looking through ZNs, likewise, mean is 11, but the median is 50%. And you can continue down. That's one of the data point that I look at, mean, median. That's one. The other one that I will look at is the standard deviation, and to look at it with reference to the mean itself and to see how large. You can see that the standard deviation for this is really large comparatively to the actual mean itself. In comparison, if I look at RM and also NOx, the difference isn't as, if you look at this, the standard deviation is almost 2 to 3 times of the mean itself, compared to this, which is only a 1/5, 25%. And then if you look at the RM itself, it's even smaller. That tells you something. With the standard deviation substantially larger than the mean itself, it tells you that the data is really, really noisy. And if you look at the likes of RM, I think this is number of room. With the standard deviation being so small, it means that your data is not as scattered and it's fairly concentrated. It's distributed around the mean itself. Then that's the data that I can have some confidence with, to play with. I know that when I actually say this is the mean, then most of the data will fall in this near the mean itself. Whereas when I look at this CRIM, hey, it can be all over the place. Later on, I'll show you some of the actual chart itself. That's where the visualization itself is really useful. So keep that in mind. I want to compare CRIM versus RM for later lessons or later part of this lesson, if not this next lesson, from the visualization perspective, so that you can actually see the vast difference between them. So those are the two things I look at, mean, median, standard deviation. And the third thing, of course, you can look at, which also describe the similar behavior of it, is the minimum and maximum, the range of it. You can see here it ranges from 0.006 all the way to 88, which is a really large range, especially when you compare it to the mean itself. Zn likewise goes from 0 all the way to 100, again a massive range. And that, so far what I've done is that I am looking at the data to itself to a large extent. The second thing that we need to understand is the machine learning algorithm itself is, when we actually try to model something, we want the data to be relatively similar from columns to columns, or in machine learning lingo, we call it features to features to features. We would like their mean to be very similar, standard deviation to be similar. That's when the pre-processing will come in. And if you look at this, you can see that the mean across the board is vastly different. Text is really large at 408, and if you look at chars, is substantially multitude, about 1,000 to 10,000 times smaller at 0.07 with the mean that way. You will have a problem, or the machine learning algorithm will have a problem, when the difference between the data is so large. And what will happen is that the movement in, for example, the text in from the actual step from 407 to 408 versus the movement in chars, which is 0.06 to 0.07, one step movement here is going to be massive in chars. And what will happen is that it will have an uneven behavior, and you're going to get unpredictable behavior when you actually don't actually pre-process or standardize the data. We will cover that a little later in our later lessons on pre-processing. That's the part whereby we standardize all of our data so that the mean are the same or the standard deviation are the same. Either way is to make sure that the movement of one doesn't suppress the other, or the movement of the other doesn't actually magnify the significance of it so much more than the other part. Right, that was a fairly long spiel, so let's dig into it a little bit. The matplotlib itself, we're going to run that. I believe, the Seaborn, we're using 0.9. Okay, so there's some basic configurations that I'm doing here. Let's see, the size has been renamed to height, so let's just do that. It's still running. Okay, how I can tell is just that asterisk there. So let's just let it run for a while. It might take a while. I believe it will take a while because it is a rather large file. I mean, we're trying to plot all 13. Is it 13 features that we have? Let me just... Yep, 13 features. We're trying to plot all 13. I think if you include the target variable, which is the median value, that's MEDV, then you are looking at a 14 by 14 matrix sort of chart. And as you can see here, it's massive and it's really, really large. I'm going to rerun this code here, having changed the height, but I'm going to skip it so that you don't actually have to watch this, take 30 seconds, 45 seconds to run. In the meantime, let me just quickly run that. In the meantime, I will describe the actual column that we are drilling in. We're going to drill in these 4 columns, but I think what I did mention earlier is that we want to actually look at specifically CRIM versus RM. So I'm going to select that, so that CRIM, and then put a comma here, and also RM. I want to actually visualize that or drill in that a little bit so that we can actually compare the difference between the two in terms of our plot. That way we have a better understanding of what I just mentioned earlier. I mean, this is way too large for us to see, so I'm going to run this again. Here we're running all 14 columns. Here we actually selected 1, 2, 3, 4, 5. Yeah, 5, and then we're plotting only 5 to study. So CRIM here and RM here. Okay, if you look at CRIM, what you can see here is that most of the distribution is down this way. If you look at RM, which is over here, you notice that it starts from 0 and 50 is here, and then it carries on substantially. And where's our room? Okay, our room is here, so my apologies. Let's start here. This is actually plotting CRIM versus RM. So I just want to look at CRIM itself as well as the RM distribution itself. This doesn't tell me what, okay, 50 is here. This is actually the y-axis. So this is CRIM plotting against itself. 50 is here, 0 is here. So you can see bulk of the data is actually distributed between 0 and 10. Each of these blocks is by 10, by the way. So if you count 1, 2, 3, 4, 5 blocks here, this roughly from, we need to drill in a little bit more to see. You can't, but this is just a really rough sketch so that you can actually get a kind of like a helicopter view of the underlying data. You can see the bulk of the data is actually distributed between here to here, 0 to 10. And if we go to the room, this is, I believe RM meaning average number of rooms per dwelling. You notice that bulk of it is actually, well, around 6 rooms, and they are really tightly banded between 4 to 8, 9 rooms. But you can see, as I mentioned before, in terms of the statistics, this is nicely distributed, really almost normal, but ultimately it's actually really compact. The data is really centered around the mean, whereas the CRIM itself has bulk of it distributed here, but there's a long tail. Although you can't see it, there's some here. And from our descriptive state, let me just hide this. Remember, we can hide this way. The maximum is 88. Although it doesn't show here, there's actually a bar here, so it actually has a really long tail for CRIM itself. Likewise with ZN, bulk of the data is distributed here, and it is actually a long tail on that side. Induced likewise is 60. This seems to be 2 mode here. Anox as well, it's not really normal. RM is what is normal. And when you actually start modeling the data using your machine learning algorithm, you do need to be mindful of this type of behavior, which is rather more challenging to model. And that's why we actually perform this preliminary EDA to really understand our underlying data, the actual behavior of it, and yeah, that's what the descriptive step is for, and as well as the visualization is for. Now I'm gonna do this once more. Let me just run those and just change this part. Because you can see I'm way too lazy to type. This time around, I'm gonna drill into another 4 columns or 4 features we want to look at. The median value is distributed fairly normal, but there's some long tail at the top end. And likewise, you can also see the other data, they are normal at all. The one thing I didn't really explain is that along the diagonal is the data plotting against itself. So this is really the distribution of the underlying data. So if you look at PT ratio, this plot with the histogram is just a plot against itself. It tells you the underlying data's behavior. The plot here is a plot of B against PT ratio. Okay, and you can see here it's weird. I don't even know how to describe it. And this is a flip of the same data, but the axis has been flipped. The axis, y-axis now is PT ratio. The x-axis is now B. So it's basically like these two are actually it's a 90-degree clockwise rotation of the data itself. So really, you can actually just look at one side of this one side of it, which is this part, rather than looking at both. They basically, the other side is just a flip of it anyway. You can see that this is not linear, and it's really difficult to actually tell what's going on between median value as well as B. It just seems like there are 2 classes of data. And notice that there's some sort of truncation around the 400, and the data seems to be all chopped up here. There seem to be it actually seems to be higher, but somehow the data collection seems to have clipped the actual data at a higher value. It doesn't seem like the data is actually very clean for this portion at all. Whereas this doesn't seem to have any relationship whatsoever. It's just random all over the place. So when I'm actually performing any machine learning modeling, if I want to actually select the features to describe my data, I want one that is actually give me some value, some information to describe the underlying data. So in our case, let me contextualize it a little bit. I'm trying to predict house price. And I want to select something that this can help me to predict the house price. Number of rooms, yep, I think that can actually help me in terms of providing some information about the house itself. Age of the house is also useful. Some things that's not really useful could be things such as, I'll just pick a random example. The month of the year, for example. I know that's a really ridiculous example, but you can see what I mean. The month of the year is not going to have any impact on the house value itself. If you actually happen to have a data that have that kind of column, which is month of the year and also the median value of your house price, you are going to see the number all over the place. It's really random. There's no relationship, much like something like this. Maybe not exactly that shape in terms of form, but that feature, which is the month of the year, will be one of those features that you will drop. This is what we meant by feature selection. Okay, you're selecting the feature to actually describe the underlying data itself. And the other portion, if I give you another example in terms of, if I want to select features to describe the face of a cat, for example, it seems like cats and dogs are still very popular on the internet, I would choose number of eyes, number of ears, those standard features to describe the actual animals itself. Selecting things such as the size of the lawn, or cat food, or those aren't gonna provide me with any information about the look of the cat or the dog. I hope that kind of like ridiculously obvious example will help you to understand that feature selection is important, and how you translate this into what we are looking at in terms of this Boston housing data set here is that it's not everything is so obvious, like the month of the year or the size of your lawn versus the feature or the looks of your cat or dogs. So what we have to rely on sometimes is statistics or visualization technique to inform us likewise. So when you actually see something like this chart here, which is the plot is, the scatter plot is all over the place, that is a sign that the underlying data has no relationship with what we are trying to predict, which is the median house value. Okay, I think that kind of like hammered that to death a little bit. I hope that has been useful for you. So I hope that actually helps you to understand a little bit about feature selection. So what we really have covered in this session is exploratory data analysis. I provided a little bit about the descriptive statistics and the necessary part about plotting, visualizing, just really playing with your data, and sometimes selecting a smaller subset of the data, the columns of data, and drill in a little bit more to get a better intuition and understand your data and look at the relevance of the data, whether you want to include it in your machine learning algorithm later, for the development of the algorithm later. With that, I'm going to stop, and thank you.